Alright, so let's continue talking about our elements and the makeup of the element with the protons and the neutrons in the center of the element, the electrons found in the orbital shells around that center, and for what we're going to look at most, there's going to be 3 orbitals. So what this does is this sets up this idea called the octet rule. So with the octet rule, the number of electrons sitting in the outermost orbital ring is trying to reach a certain level. That way the outer ring is complete and the electrons fill every space in the outer ring or outer shell, and that element is stable. So let's take a look at the common ones that we're going to talk about. Hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, or CHONPS. And based on what we can determine from the atomic mass and the atomic number, we can figure out the number of electrons in each of these. So hydrogen has 1 electron. This means it's going to sit in this first orbital shell. That's where it's going to go. It's going to float around and sit in that first orbital shell and try to balance out the protons and the neutrons sitting in the center there. The problem is, or not the problem, but the way this works is the first orbital shell ideally wants a second electron right over here to be balanced. So things to remember, the first shell, let me do this with a text box, it'll be a lot cleaner and easier for you guys. Okay, so the first orbital shell holds a maximum of 2 electrons. Alright? So that's why hydrogen is looking for 1 more electron, because it wants to get 2. It wants to have a full orbital shell. So this often causes hydrogen to attach to other elements, to bond, because it's trying to fill this space right here with another electron. Now if we go and look at something like carbon, notice carbon has 2 electrons in its first shell. So its first shell is complete, it's happy, it's stable, it's doing what it needs to do with the first shell. But the second shell, the second orbital shell holds a maximum of 8 electrons. So this poses a problem for carbon. Carbon, we got 1, let me do it in the pen, we have 1, 2, 3, 4, but it needs to get to 8. That's the octet rule. It wants 8. So carbon needs 1, 2, 3, and 4. Carbon wants 4 more in order to be complete. So this is what will often cause carbon to bond in certain patterns, is its desire to get 4 more electrons in forming bonds. We look at nitrogen. First shell is complete. We're good here. We're good here. 1, 2, 3, 4, 5. It's trying to get to 8. So we need 1, 2, 3 more, and then nitrogen is complete. Go to oxygen. First shell is complete with 2. 1, 2, 3, 4, 5, 6 in the second shell. Oxygen needs 2 more. So again, nitrogen needed 3. Carbon needed 4. Oxygen needs 2. And then that's going to make oxygen complete. And oxygen is going to have a full outer shell. Step up to phosphorus and sulfur. Phosphorus and sulfur have enough electrons to make the first shell complete. It's got its 2. Then it has 8 in the second shell. And it's happy, it's complete. Its second shell is filled. But it has 5 in the third shell. So what we're going to see when we look at The third shell, it also holds a maximum of 8 electrons. So if you go to a third shell, you still need 8 in that third shell. So phosphorus has 1, 2, 3, 4, 5. It's going to need 1 there, 1 there, and 1 there. It's going to need another 3 in its third shell to make it complete. We jump over to sulfur. Sulfur has 3 shells. First shell is complete. Second shell is complete with 8. But then when we count up how many it has in the third shell, we got 1, 2, 3, 4, 5, 6. Sulfur is looking for 2 more. 2 more will make sulfur complete. So because of how many electrons are sitting in that outermost shell, and it doesn't matter if the outermost shell is 1, if it's the second shell or the third shell, all these elements are trying to reach a level of completeness. Again, this is what drives bonding between the electron, or between different elements. This is what creates our different bond formations to create water, carbon dioxide, ammonium, methane, etc. Okay, so let's take a look at an example where we have 2 elements coming together to try to complete their outer shells and forming what we call an ionic bond. Now, in an ionic bond, this is when one element will steal or take electron, sometimes it's more than one, will take electrons from a second element. Okay? So the second element will lose them, one will steal and gain, one will lose or give up, creating an ionic bond. All right, so here's a very, very common example of an ionic bond we are dealing with and using daily. Sodium chloride. So if we go back to our periodic table, just briefly, sodium and chloride. Sodium, right there. Chloride, over here. We have 11, we have 17. If we took a look at their atomic masses, atomic numbers, from that information we would determine the number of electrons. Sodium will have 2 electrons in the first shell. It will have 8 electrons in its second shell, but it has 1 electron in that third shell. That's the problem. Sodium's got 1 right here. So to fill the third shell, sodium needs 7 more. So trying to get 7 more electrons, that's going to be pretty tough. Chloride, on the other hand. Chloride, first shell has 2, second shell has 8, third shell, 2, 4, 6, 7. Okay? So chloride has 7 in its third shell. It needs 1 more. 1 more electron. And chloride is happy. So what it's going to do is it's going to steal that electron from sodium. That's going to move over to chloride. So right here, that is the electron that used to be over there in sodium. So when chloride steals it or takes it or gains it, it now fills its outer shell. If you look at sodium, sodium got rid of that 1 electron that was sitting out there by itself in the third shell, reducing down to just 2 shells. Now the second shell has 8 here. Sodium's happy, chloride's happy. This is what caused these 2 elements to come together in an ionic bond. So think about bonds like relationships. If somebody's stealing or taking, you're going to have a relationship, but it's not a real strong one. It's not one that you always want to be in. It's not a very stable type of relationship. It does form. It does create a bond, but there's not a lot of energy holding this type of bond together. So when we look at the life example, salt, sodium chloride, table salt, it's formed because of an ionic reaction. But if you throw salt into water or give sodium and chloride other options to bond with, they're going to break apart and do what we call dissociate rather quickly and rather easily. Okay, so that's our first type of bond or reaction, is the ionic. One element will gain, one element will lose, but it pulls them together and they form this bonding relationship. Alright, so our second type of bond is called covalent. This is when elements will share electron or electrons. Sometimes they share one, sometimes they share two, sometimes they share three. At most three. You're never going to see them sharing four. Okay, so that is a type of relationship that has greater strength. You share electrons, you mutually work together, you both benefit. Seems like a good thing. Now we will see in the covalent world there are two types of covalent bonds. One is called nonpolar and one is called polar. In a nonpolar type of bond, nonpolar covalent bond, there is an equal sharing of electrons, 50-50. Okay? Equal amounts, 50-50. Each element shares one electron and receives one, equal exchange. Very, very strong relationship, strong bond. In a polar covalent bond, there is a slightly unequal sharing of the electrons. Let's call it a 60-40 relationship. It's not the ionic 100% zero. It's not the 50-50. It's a little bit off. Still closer to why we call it covalent versus ionic. It's a 60-40 relationship. Still a strong relationship, but not completely equal. A little bit unequal here. Okay, so when we look at examples of covalent bonded molecules, things like hydrogen as a gas, H2, they each share one electron from the other. So this hydrogen shares its electron with that hydrogen, this hydrogen shares its electron with that one, and they're both happy. And this forms hydrogen gas, H2. If we look at oxygen, let's zoom back up here for a second. Oxygen, when we look at that with the atomic, the model of the atoms, oxygen is looking for 2 more electrons. Because it has 6 electrons in that outer shell, it wants 2 more. It's trying to reach 8. So what oxygen often does is it shares 2. It shares 2 of them from this oxygen, 2 go that way, and 2 go this way. And that's what's represented by what we have here. Okay, so the right oxygen shares 2 with the left oxygen shares 2 with the right, and that is what gives us O2 as a gas. This is what we have to have. This is essential for our breathing, our survival, our life. We have to have oxygen gas. So that is an example when you have 2 of the same elements that are sharing oxygen gas, hydrogen gas. There is a triple covalent bond. And the example we see with that is when you have nitrogen. And nitrogen shares 3 of its electrons with another nitrogen. And that forms N2. I'm not going to try to draw out the orbitals with the mouse. It would not be pretty for you. But when we look at nitrogen as a gas, it needs 3 more electrons here. If it bonds with another nitrogen, it'll share equally 3, creating a nonpolar covalent bond. Strong, strong type of bond. So bond strength is important because when you break it, it releases energy. Thus, when we look at the bottom here, we have methane, lots of bonds, Methane's got a lot of energy in it.